Hey everyone, I'm John. I'm one of the co-founders of Succinct. We work a lot on making zero-knowledge proofs really easy for developers to use. And one of the biggest initiatives that we've been focusing on in the past year or so is real-time proving. I'll go more into detail about why real-time proving is so interesting, but it has a lot of really great implications for Ethereum and the roadmap, so I'm super excited to deep dive into it. So to start off, what is real-time proving? I'm not sure everyone in this crowd has heard this term or even knows what it means, so I wanted to spend some time defining what it actually is. So the TLDR is that it's the ability to generate a zero-knowledge proof of executing any arbitrary Ethereum block in under 12 seconds. Now, the reason why generating zero-knowledge proofs of this computation is interesting is because zero-knowledge proofs have this magical property, which is that no matter how complex the computation you're proving is, the verifier actually only takes constant time. So in practice, right, you can imagine that you have some computation. It takes tens of seconds or minutes on your laptop. If you're able to generate a zero-knowledge proof of that, the verifier just takes this proof, it just runs some code, and within tens to hundreds of milliseconds, it can verify that this computation had some output. So in the context of Ethereum, this technology has actually already been used. There's a lot of these things called ZK rollups, which use this property to settle batches of transactions on L1. But real-time proving is really interesting in the context of the L1. So let me go a bit deeper into that. So today, with Ethereum L1, we kind of have this block building pipeline. We have this situation where block builders bid to submit blocks to a proposer. Proposers send blocks to validators, who then execute that block. Then these validators basically check, hey, did the proposer submit like a valid block? They vote on it. And one key thing in this entire pipeline is that there are like these physical bottlenecks to the system, which and one of these biggest bottlenecks is like actually the amount of time it takes to execute these transactions. And this kind of upper bounds the potential TPS of Ethereum. So with Ethereum in particular, the community and when Ethereum was started, it had these certain values, mainly around decentralization. So one of the key things that the Ethereum community cares about is that these validators don't have like intense hardware requirements. So you can imagine like, hey, if for example, with a chain like Solana, they have very few nodes. They have very high hardware requirements for the chain, and that's how they increase the TPS. But in the Ethereum setting, we're really bottlenecked by like the minimum hardware requirements of the validators that are performing the chain. Now, simultaneously, the Ethereum community kind of recognizes that, at least in the L1 market, it's really important for Ethereum to scale to much higher TPS, like 10,000 millions of TPS. So there are these pretty influential Ethereum researchers like Dankrad who are proposing these EIPs where they want to increase the gas limit by 100x. But then again, there's this open question of how do we increase the gas limit by 100x while maintaining these values of decentralization? So this is where real-time proving comes in. So the EF and the Ethereum community in general is really excited about real-time proving right now because it's able to solve this exact problem. Instead of increasing the hardware requirements of the validators, you can instead generate a zero-knowledge proof of the transactions that are being executed. And then you could imagine even the weakest validator in the network, maybe even a Raspberry Pi that's like only $35, could be verifying 10,000 transactions per block. So we've kind of broken this trade-off of like the hardware requirements and the number of transactions that are possible to prove with zero-knowledge proofs. And there's actually a lot of excitement about this idea, even outside of like more of the nerdy types in the Ethereum community. So for example, like Kathy Wood and one of her analysts suggested that this was a really promising direction for Ethereum and that it was a great way to become competitive in the L1 landscape. So to be pretty concrete, what does real-time proving actually look like in the block building pipeline? Well, we keep most of the things the same, but the main thing that changes is that now when the block builders send the block to a proposer, instead of just sending the block, you can imagine they bundle it with a zero-knowledge proof. And then downstream of that, all the validators, instead of re-executing the block, they just verify the proof. So just with this one change alone, we now have a situation where verification of the transactions just takes milliseconds. It's going to enable us to scale the gas limit by 100x. And you can imagine that if this technology exists, we could even be more ambitious with the L1 scaling roadmap, achieving even more ambitious targets. Now, personally, I think real-time proving is one of the most key technologies that we need to develop over the next year for Ethereum to be on path to becoming the world computer. When we increase the TPS, we're going to be able to host more ambitious DeFi applications like CLOBs. We're going to be able to settle more rollups that are operating at a higher TPS to the L1, which will be really great. But simultaneously, I do want to emphasize that there are other things that we need to improve on as well. For example, we need to reduce the block times. We need to increase the DA capacity of the L1, and also solve L2 interoperability and finality. Nonetheless, at Succinct, as a company really focusing on zero-knowledge proofs, I think this really strong motivation, I think not just with our company, but in the ZK space generally, this real-time proving problem kind of became like the space race of the ZK space. So this is like something that many, many teams are focusing on solving. I think at Succinct in particular, we felt very naturally suited to work on this problem. One of the key open source projects we maintain at Succinct is this SDK called SP1. It's something known as a RISC-V ZK VM. The high-level explanation of what it does is it's able to take any existing Rust or C code and run it inside of a proof system to generate a proof. And SP1, because it's able to do that, has become really popular with developers who just really want to go 0 to 1 with ZK as fast as possible. Because when you use something like SP1, you don't need to know anything about cryptography. It's super easy to set up. And you can also reuse libraries like Alloy or Foundry and the existing Rust Ethereum ecosystem. We actually have a lot of adoption. We're used by 35+ protocols. We have thousands of GitHub stars. So overall, we were like, hey, SP1 was really great because it made using ZK easy. It made it very performant. But what if we could also bundle in this product the ability to prove Ethereum in real time? And in general, the improvements we would make for proving Ethereum in real time would also generalize to other computations, which is what made it a really interesting research problem for our team. So one thing that we benefited from, we kind of had a jump start, which is that we were already using SP1 to prove a lot of Ethereum blocks for L2s. And this was actually really easy for us to do. And I have to do my shameless Reth plug. But you basically just compile Reth to a binary, to this standard called RISC-V. It's an open source ISA supported by most compilers like LLVM. And you literally just take this binary and you run it in SP1. So we kind of already had this end-to-end pipeline for proving Ethereum, and it was really easy. Now, one difference that's worth noting about this pipeline compared to like the past is that a lot of the teams that you might be familiar in ZK, like Starkware or ZK Sync or Scroll, what they did is they actually like kind of embedded the binary into the proof system itself. Right? So they actually like kind of designed a circuit in a ZK proof system that was specifically designed for proving Ethereum. But one thing that's really worth emphasizing here is that we're able to take existing code, like the Reth execution client, and just run it in SP1 and get a ZK EVM out of the box. Anyways, so for the past 6 months, we developed a new version of SP1. It's actually called SP1 Hypercube. And we kind of, in the early days of SP1's development, we were really focused on usability and cost. But when we realized that real-time proving was a really big thing that we need to optimize for, we realized that a lot of the design decisions and the engineering decisions we made with architecture could be adjusted to be much more performant with real-time proving. So I don't want to get too deep into the technical details, but we had to do like a lot of moon math engineering to make this happen. So for example, on the proof system side, there are really popular existing proof systems, such as Starks, that are used in a lot of the most popular ZK projects. We kind of had to replace that with some new math that our research team developed. We really had to push our data center operations. Right now, we run like thousands of GPUs on AWS to coordinate really large proving jobs, but realized that the GPUs on these clouds are too slow. So we actually had to scale up like these third-party data centers. We had to use like consumer graphics cards, figure out how to optimize the GPU performance on them, and really like pick out all the low-hanging fruit of performance. And then on top of that, there's a bunch of stuff like pipelining, scheduling, all the classic performance acceleration stuff that you have to do. Let's see. So this is a visual that we made visualizing our release in May 2025, where we released an early preview version of SP1 Hypercube. And what this animation is showing is it's actually showing us proving Ethereum blocks in real time on a cluster of 200 GPUs in Nebraska. And what each of these bars are showing, it's showing one task running on one GPU that's like processing a section of the proving workload. And oh, sorry, I guess I can only play it once. But so each of those lines was showing a proving task that was running once. And you can see that we're running many of these tasks in parallel. The tasks are constantly streaming in. And to even get it to that latency took a lot of engineering on our end. And you could see that for some blocks, we were able to prove them under like 6 seconds. Now, these are some concrete benchmarks we ran across 3 months of blocks on Ethereum from April to May. We like uniformly sampled, I think, around 10,000 or 100,000 blocks. And we ran this benchmark where we basically ran SP1 Hypercube on these 200 GPUs to see like how close we were to this objective. So as you can see, we were actually able to prove 93% of the blocks under 12 seconds. Now, you might be asking, like, what is going on with the remaining 7%? Well, what we found is that actually for the remaining 7%, the main problem wasn't that SP1 Hypercube was too slow, but it was rather that the Ethereum gas pricing schedule was in some ways divergent from the costs our prover was paying. So for example, there's certain precompiles on the EVM which are really expensive to prove, but they're not properly priced in the gas schedule. So just by adjusting this gas schedule, we think we could get this very easily to 99%. And it's also worth noting that these are benchmarks from a few months ago. We've improved the performance a lot by then, so that should help as well. So I think I really want to emphasize that this real-time proving objective was kind of like a moon landing moment for ZK. And I think if you asked many people working in this industry a few years ago if this was possible, they would tell you it probably wasn't. For some context, in 2023, when a lot of the first ZK L2s came out, the amount of time it took to prove an Ethereum block was on the order of tens of minutes. But with each generation of new ZK technology, we were able to get an order of magnitude improvement on latency. So you can see with SP1, which was released around February of 2024, we got the proving down to a few minutes. With SP1 Turbo, which came out around December 2024, we got it down to tens of seconds. And with SP1 Hypercube, which came out early 2025, we finally got it under 12 seconds. And I think in general, there's kind of this Moore's law type of behavior going on in ZK right now, where with every generation of technology, we are not seeing the gain stop. There's a lot of low-hanging fruit. And I think it would be potentially not surprising if we got real-time proving down to even a few seconds or less than a second within 12 months. Now, in terms of the economics, I think this is something worth discussing because if the amount of money it took to generate these real-time proofs was unreasonable, perhaps we could not use them for Ethereum L1. But even today, the actual economics of real-time proving are really good. The amount of money you need to set up one of these clusters is only around $300K today. And we think that with more performance optimizations, we could get it to around $100K. Now, there's also some variable electricity costs that need to be paid for. We haven't benchmarked them, but we don't think that they're going to be a huge bottleneck. But in general, I think the economics of real-time proving are very approachable and will only continue to become more and more accessible. Now, in practice, while this technology is being developed by many ZK teams, there is an open question of how we actually integrate this technology into the protocol. I think earlier in my talk, I described a bit about how we might insert it into the block builder pipeline, but I did not answer many questions. For example, who is going to provide this proof? Where are they going to get it? Will we like enshrine one ZK VM, or will we have many ZK VMs? And are there any weird game theory or mechanism design problems with introducing this into Ethereum? So there's a lot of people looking into this right now, especially since the EF is so interested in it. And one interesting problem that I think people immediately realized is how do we solve the problem of block builders adversarially choosing blocks that are really hard to prove to halt the chain? So this is like an example of like a technical problem that we need to solve. Now, one proposal that I've already seen is this idea of forcing the block builder themselves to actually introduce the proof into the pipeline. And this would be kind of a good thing to do because it would align the incentives of the block builders with the chain itself, which is to not halt. So that's one interesting idea. Now, in terms of how to get the proof, one potential option is like that these builders actually set up these clusters themselves. I said that it was around 300K. Maybe it's not crazy for these people to be operating these data centers. Now, another option is we could create an external protocol, kind of similar to MEV Boost, where we externalize the proving work itself to a marketplace. So one emerging concept in blockchains right now is this concept of prover networks, which are these permissionless two-sided marketplaces for proof generation. And you could imagine that these Ethereum builders plug into such protocols. Maybe they have assets or predefined off-chain agreements to outsource these proofs to these data centers. So in terms of the flow, you could imagine it something like this. So these builders are already running a code to build these blocks. They could run a sidecar similar to MEV Boost, like maybe let's call this ZK Boost. This external protocol could actually conduct an auction where many provers around the world are bidding on these proofs and generating them. If you have an auction, one thing that's great is it's a naturally competitive market. So these people are going to, over time, drive the costs down, drive the latency down, and make this much more affordable for users on the L1. Then you can imagine the prover network enforces that these provers have to generate the proofs within some deadline, maybe a few seconds. And you can imagine then that proof gets sent back to the builder, which gets bundled before they send the result to the proposer. So that's one potential way this could be all integrated in Ethereum. But again, I think these are really open questions, and they need to be discussed by the community. So that's about the end of my talk. I think I covered everything I wanted. But in general, the key things I wanted to focus on is first, that real-time proving is this really incredible technology that's being built by the ZK teams right now. And I think it's going to really solve a lot of the scaling problems that we're having with the L1 right now. The technology is in some ways already here. SP1 Hypercube, the latest release of our ZK VM from Sysynced, is already able to achieve 93% of Ethereum blocks. And then finally, I think there's a lot of open design decisions and research questions that we need to solve related to the mechanism design and game theory of how to integrate this into L1 and make sure it's as robust and reliable as possible. Cool. That's about everything. If you have any questions, now would be a great time to ask. Thank you so much.
Yeah, great presentation. So, like, you're talking about all these real-time proving, right? Like, we can see that right now, probably we can already achieve like super fast proof generation. Then, regarding the cost, can you share some data points, like, for example, for the past few months and probably for the next few years, how cheap we can achieve, like, when we do the real-time proving for all the L1 transactions?
Yeah, that's a great question. So the EF actually has this website called ethproofs.org, if I remember correctly, where there's actually public continuous benchmarking of how expensive it is to generate these ZK proofs for Ethereum transactions. I think right now, the average proving cost ranges between 1/100th to 1/10th of a cent per transaction. And depending on the gas limit of the blocks, depending on what chain you're on, these things change, and also the transactions that are being proven. But I'm very optimistic that for the average L1 user, this is already a technology that is going to be very affordable, and it's almost going to be unnoticeable compared to other costs like DA. Yeah.
Hey, thanks for the call. I was wondering, like, the 300K, is it per year, per month? Like,
it would be like a one-time cost. So you can imagine, let's say you need like 30 GPUs or 50 GPUs to prove Ethereum. It's just like that times the number of GPUs you need, the number of motherboards, the number of RAM sticks you need. That's kind of how we're getting the 300K number.
So it's on premise. It's not running from the cloud.
Yeah, in the cloud, actually, we found that the markup is like insane, largely because NVIDIA actually like nerfs the cards on the cloud intentionally to get more margin. So we found that if you use these consumer graphics cards like the 3090s or 4090s that are quite available, you can get great cost efficiency, and it's just much more affordable. It's kind of brain dead not to do it. Yeah.
I think it's only been since this week, since you guys launched it, but has there been anything interesting that's taken place from the launch of the Prover network?
Yeah, there has been some interesting market behavior. I think at first the provers were competing, but now that the provers are getting a little bit more sophisticated, I think some of them are like colluding to like make the price a bit higher, which is something we observed. So we're trying to onboard more provers, encourage more perfect competition. I think it's always really interesting to deploy these things in the wild with real money because you start to observe these behaviors. I think it'll take some time for us to nail it, but the prices on the network are actually already very competitive with our like Web 2 equivalent APIs. Yeah.
I have a question about this 7% of blogs that you cannot prove in real time. What exactly is the precompiles or what exactly the opcodes exist in these blocks that you cannot do?
Yeah, so in ZK VMs in general, even if you just think of it in terms of computation, there's different costs compared to like just real hardware costs. So for example, on a real chip, when you move data around, you actually have to like think about how far is the data. Like, am I going to the registers? Am I going to L1, L2, or like just RAM? In ZK, like all of that is not true. There's no concept of caches really. It's just like the amount of time it takes to store a value and retrieve a value. So that's already very divergent. Where like storage in general is like already mispriced. In particular, with like hash precompiles like Blake, 2, SHA, and Ketchak, you have to be really careful. Because right now in SP1, we have accelerators for SHA and Ketchak, but I think we're just in progress of implementing one for Blake 2. So when users on the L1 spam the Blake 2 precompile, it's really easy for the proving costs to explode and the latency. So these are the type of like, you kind of have to like whack-a-mole all the problematic opcodes and stuff and solve them in the ZK system and also in the pricing layer. So that's what we found.
Hey, really great talk. I'm back here, by the way.
Oh, okay, what's up?
You've thoroughly convinced me that we're making great progress towards real-time proving. The one thing that still concerns me a lot about the ZK work is the potential for soundness errors. This stuff is so incredibly complicated, and like I'm personally unable to like vet the circuits myself, right? What are you doing there to like convince me that I'm not able to generate a fake proof, for example, very efficiently that shows that all your money was transferred to me?
Yeah, I think this is a really great question. Yeah, I think in practice, many ZK systems that have been deployed, there have been bugs found in production, and there's no reason not to believe that this wouldn't be true in the future. I think one thing that is changing right now that is really promising is the development of formal verification tools and automatic bug finding tools. The EF is very serious about this, actually, and they're funding a lot of really great work and really great formal verification researchers to discover these bugs. I think even in the past 6 months, these tools have gotten a lot of better. And I think in particular with Picus, which is a determinism checking tool from Verdice, they found a bunch of bugs using that tool. I think there's another team from Europe, I'm forgetting their name, who also built a fuzzing tool that found some bugs. But in general, if you want to get the perfect soundness, I think formal verification is the ultimate answer. It's actually not that much money to generate lean proofs of these circuits and verifying that they're correct. It's actually not that out of scope as well to formally verify the proof systems themselves and the fact that like the Rust code is secure in terms of soundness. So I think that is the #1 way we can get to 100% confidence that these systems are secure. Cool. Thank you.